Ever wondered how neural networks really process information as they get deeper? Today, we're diving into a groundbreaking study about ReLU networks, those ubiquitous layers in AI that help models learn complex patterns. But here's the twist. Researchers uncovered something surprising about how these networks handle information as it passes through each layer. Let's start with the basics. A neural network is like a team of filters, right? Each layer transforms input data, trying to extract the most useful features. ReLU, or rectified linear units, act as gatekeepers. They let positive values through and zero out negatives. Simple enough. But here's the thing. When you stack these layers, something weird happens. The effective dimension, a measure of how much information is preserved at each layer, starts to oscillate. Think of it like a wave. As data moves deeper, the network loses some information, like a signal weakening. But then, surprisingly, some of that lost info comes back. It's like the network is reviving parts of the original data at certain depths. So how does this work? The study analyzed what happens when you feed a fixed set of inputs through a network with random Gaussian weights. They found that the rank of the activation matrices, how many independent directions of data are preserved, follows a precise mathematical pattern. The key formula: the expected effective dimension at layer L is roughly m multiplied by 1, 1, 2 slash pi, letter 2, 1, 1, 3, where m is the number of inputs. The decay factor 1, 2 slash pi, tilde 0, 36, means the rank deficit shrinks geometrically with each layer. But here's the cool part. At specific depths, the rank peaks again, creating these revival points. Why does this happen? It all comes down to the random nature of ReLU. Each layer acts like a random Bernoulli mask, zeroing out half the data on average. But deeper layers introduce new randomness, which can partially restore lost dimensions. However, this oscillation only occurs in finite-width networks. If you use orthogonal weight initialization or a modified ReLU with a strong negative slope, the rank stays nearly full, no ups and downs. Now let's shift gears. The study also explored Leaky-ReLU, an activation function that allows a tiny slope for negative inputs. When this slope is extremely steep, something fascinating happens. Normally, layers cancel out certain patterns through interference, like waves canceling noise. But with this modified activation, those cancellations break down. The result? The network's effective dimension drops more slowly as layers increase. Practically, this means deeper networks can retain more unique information, avoiding redundancy. Imagine building an image recognition system. If each layer adds new, independent features, the network becomes more powerful. But if layers overlap too much, it's like redundant steps in a recipe, wasting resources. This research shows that with the right activation function, you can slow that redundancy, keeping the network's capacity higher for longer. The math behind this involves probabilities and expectations. The authors used inclusion-exclusion, a technique for counting overlapping groups, and transformed the problem into an integral involving the gamma function and a modified Hurwitz zeta function. By analyzing this integral in the complex plane, they identified key poles where the function behaves unusually. The residues at these points revealed oscillatory behavior tied to the matrix structure. The final step was proving that leftover terms decay exponentially, confirming the dominance of these two key effects. This approach, combining complex analysis and probability theory, uncovered hidden patterns in matrix rank behavior. So what's the big takeaway? By leveraging tools like Mellin transforms and residue computation, researchers uncovered how neural networks balance information loss and recovery. This work not only deepens our understanding of network dynamics, but also hints at new ways to design more efficient architectures. Next time you see a deep learning model, remember, its layers aren't just stacking transformations. They're dancing with probability, reshaping information in ways we're only beginning to understand. Thanks for watching and stay curious.